I'd like to welcome you to Research Pays Off, and I will introduce our speakers for today. We have with us Maria Maston, who is the State Concrete Engineer in the MnDOT Office of Materials and Road Research. She has previously held positions as a student worker in the MnRoad Research Section and Pavement Management. She graduated from the University of Minnesota in 1996 with a Bachelor of Science in Civil Engineering, and she is a registered professional engineer in the state of Minnesota. Ms. Maston has worked at MnDOT for 25 years, and she was the previous chair of the National Concrete Consortium from 2013 through 2018. And then joining her is the PI of the project, Dr. Peter Taylor. He's the director of the National Concrete Pavement Technology Center at Iowa State University. He is involved in conducting projects and programs investigating materials-related aspects of concrete pavements. He also spends time helping agencies and contractors implement best practices in concrete pavement design, construction, and maintenance. His research is focused on developing mixtures that are engineered to meet the requirements of the environment that will be used in. He's a professional engineer registered in the state of Illinois and an active member in a number of professional societies. So they're going to be talking about their construction report for jointless FRC roundabouts in Minnesota project. And I know they've got a lot to discuss, so I will hand it over to Maria to get started.
All right, everything look good, Lauren?
Yep, and I can hear you, so we're all set.
All right, sounds great. Thank you. Thank you, everyone, for joining us today. As Lauren said, we're going to give an update on how the fiber reinforced concrete jointless roundabout is performing in Minnesota. So just before we talk about that, I just kind of want to give you a history of fiber reinforced concrete and paving in Minnesota. And MnDOT's first real experience was back in 1993, where we have some test sections installed in southern Minnesota, District 7 actually, which is where the roundabout's also located, 5 to 6 inches, and then another project 4-inch to 6-inch thick. So our general history of use of fiber routes is in concrete pavements that are anywhere from 3 to 6 inches in thickness. And so in 1993, we started out. In 1997, we tried it on some intersections and installed our first test cells in MnRoad, 6 different test sections. In 2004, we added 4 test sections to MnRoad. In 2008, we installed 4 additional test sections. And in 2017 and 2018 is when we really started to install fibers actually out really more on our network, intentionally installing them in full projects. And so we do have built a couple pavements since then, I believe, that have fibers in them, but our first 2 projects were Highway 63 and Winona County CSAH 25. And actually, as part of this project, there were construction reports written for both of these 2 projects also that would be available on our NRRA website. The fibers have evolved. Some of the first fibers that were used were these polyolefin fibers. And so they were really thick and they didn't bend very well. Any of you have ever seen this, you know, people would love to play with this, push it up and everything. But anyways, these are very stiff fiber. And then we also tried some polypropylene fibers, which are really the complete opposite of the polyolefin ones. And they're very light, very light and very small. And so those are just some of the first fibers we tried. And then we will, I believe, talk a little bit more about the fibers that were actually used. Give you an idea just within the state of Minnesota where these fiber reinforced concrete pavements were installed. As I said, these first few pavements were installed down in District 7 area. This, of course, is Min Road up here. These were the two first network type projects that we installed them on the entire length of the project. And then down here in southeastern Minnesota is where this fiber reinforced roundabout is. So what came of this is District 7 has been using roundabouts as a pavement solution for several years, but one of the things that's been bothering them is the complication of the jointing pattern and getting that all you know, right. And so they really said, well, what can we do differently? And so that's one of the things we'll talk about. Give you an idea. The roundabout was actually constructed, you know, there aren't really any houses or anything around it, but what the necessitated it was a lot of people took a shortcut from New Ulm over here to Highway 68 and didn't want to go all the way in through Sleepy Eye, so they decided that it would be best to potentially build a roundabout right here. So this I'm not going to show you, but this is just a YouTube video is available if you really want to get in and look at the overall project. This is the link for the YouTube video. Really gives you a good outlook, though. You can see that the legs that come in and out of the roundabout, those are all jointed. And you can see in the actual roundabout that it was constructed without any joints. You can now see there are some cracks in it, and that's definitely one of the things we're going to talk about today. But there were no joints intentionally constructed in this roundabout at all. So why build a jointless roundabout? So as I said, District 7 Materials contacted us. They contacted us with the idea of doing a continuously reinforced concrete roundabout. As I said, they didn't want to worry about the jointing pattern. I had a lot of concerns about the cost and constructability of doing a CRC roundabout, because for those who may not be familiar, basically a continuously reinforced, there would be steel running really in a circle all the way around the roundabout to hold it together. And it did seem to me to be maybe the most cost-effective option. And constructing it, just that gave me some concerns too. So there was actually a presentation at the National Concrete Consortium meeting discussing fiber reinforced concrete roundabouts that prompted the idea to build around an FRC roundabout without joints. Could the fibers in the concrete provide that load transfer that we normally see with the dowel bars? So lots and lots and lots of discussion ensued. But what we ended up with was not doing a CRCP, but was to try this jointless roundabout. So we followed, when we started using fibers, we were following along with Illinois specifications for fibers. However, we knew that we needed to have a fiber that, my term is going to be tougher, but that had a higher residual strength than the standard fibers that we were using in most of our projects. So we actually required a mean residual strength of 175 PSI when tested in accordance with ASTM C1609. So they had to give us test data to prove out that the dosage of the fibers was going to achieve this residual strength. And then there were a few other criteria besides C618, the length of the fibers and the aspect ratio. Those were two other criteria that were controlled, but the overlying criteria was this mean residual strength. So on the Highway 4 roundabout project, the contractor that constructed it was Hoffman Concrete, and Semstone was the supplier of the concrete. The contract required a test date to provide in that test data and to do a test pour. So they started out and they did a test pour. The initial fibers they submitted, they did not demonstrate to us that it met the 175 PSI. So they actually had to change the fibers to achieve it. The dosage rate they ended up with was 6 pounds per cubic yard. And the fibers they chose were a synthetic micro and macro fiber. is their end result fibers. They actually, with their test pour, the first time they poured it, man, they worked hard to try and get it finished off and everything in their trial pour. So they ended up making a few adjustments, and we required them to do another test pour. So that was the fiber requirement. We also required a quality control plan for incorporation of the fibers. So we wanted, you know, we've used fibers before, but we didn't want to have clumping. We just wanted to have a good sound plan in place and for everyone to think about it ahead of time. So as part of their QC plan, they had to identify the dedicated personnel involved in introducing the fibers to the mix. They needed to provide the proposed method for adding their fibers to the mixer, and so that we could be ensured that they get mixed thoroughly, and they needed to provide mitigation strategies if unmixed fiber balls were identified. So, and then, so they did provide a quality control plan. We required, as I said, the trial batching, a minimum of 5 cubic yard trial placement, so test pour, I should say, with a contractor design mix. So that we wanted to make sure before we got out on the road, because we wanted a jointless roundabout, that they had the mix dialed in. So they had to demonstrate their slump, air loss, and workability. Any trial batching was included in the cost of the concrete roundabout. It was not an additional cost that we provided. We also required that the manufacturer's technical representative was available to troubleshoot any issues we may have with introducing fibers. And I understand fibers are not, adding those to concrete are not a new thing. I think 4 pounds per cubic yard is pretty much every day of the week, probably for a lot of concrete producers. But once you start increasing the dosage rate, as we saw at Minroad, it stiffens the mix up, and it does require additional mixing and those sorts of things. So we wanted to, like I said, work the kinks out. So the placement requirements, we required in the contract for them to place it in one continuous placement. So when I talk about that, you know, in my mind, they were going to start, and I think I'll have a picture coming up. They were going to start on one side, and they were going to go around in the circle. And what the contractor chose to do is to truly give me a jointless roundabout, which I assumed I had already surrendered the idea that I was going to have one joint in it, but they truly intended to place a jointless one. So, so that was one of the requirements of the contract. Another requirement, you know, we got lots of experts across the country who are knowledgeable and joints and cracking and pavements, and there was really a lot of nervousness about leaving this pavement with absolutely no crack controlling on it and just letting it crack where it was. So the decision in the end was made that we were going to provide notches on the outside edge of the roundabout. So they would saw in these notches, 15-inch long at a depth of 1.5 inches. I believe the roundabout was 8 inches, I think. Every 4 feet on the outside edge of the roundabout. So if that was at a minimum, we were attempting to control our cracks. If they were to occur, we were going to try and at least, you know, get them spaced out as best we could. We also required them to seal those notches using a hot pour material. Like I said, one of the requirements was for one continuous placement, and like I said, they did more than what I thought they were going to do. So you can see right in between the two ready mix trucks is where they started, and they actually had the trucks deliver, and they had 2 crews at the start of it to get going, so that one truck could dump and one crew could work this way around the circle, and this truck would dump and work this way around the circle. So they actually, like I said, very unique, but they did set it up so that there would be no cold joints. We did have a few issues with delivery of trucks, so there was some time waiting, but they did absolutely design it with build it without any cold joints. These are just a few additional pictures of the concrete placement. You can see there's a few crew members over here. A lot of people there were a lot of people on site to accomplish this. Like I said, there were 2 crews. And so you can see they're going that way and they're going this way with it. So the mix was a little, it was a little stiff. We can talk a little bit more about that. But generally they didn't have issues consolidating it. In fact, we didn't really use internal vibration, and I'll show you why coming up in a minute. One of the things that I had to chuckle about was you're building concrete in a circle. Well, in southern Minnesota, it's wide open in areas, and this happened to be one of those areas, and the wind was blowing like crazy that day. So the interior truck apron was colored concrete. So depending upon the way the wind was blowing, when they were curing it, it was easier and sometimes it was harder. So luckily they had all those guys there on site, because a whole bunch of them were able to hold the plastic up so that when they cured it, the cure did not get onto the colored concrete. So I was impressed with their ingenuity on this project. This is just a closer up picture of the vibration of the concrete. Like I said, there were a lot of hands on deck. They used a portable vibrator and a roller screed. They were using a hand vibrator and putting it in, but the problem we were having was that the fibers were nesting. As they put it in, the fibers would kind of grab on the vibrator, and so as they pulled out, they would have these little, it almost looked like a bird nest, and so that's kind of where we got the nesting term from, of the fibers. So we decided that we weren't going to use the hand vibrators for vibration anymore, but we did use them limited in the areas between the loads so that we would not have that that cold joint in there. So there were definitely decisions and adjustments made on the fly as we were doing this project. This is just a visual of the roundabout. The legs were poured on 910. So all these legs were poured and jointed. Kind of funny, the contractor did not put joints in this, and so across every one of these really skinny areas in the legs, they actually ended up with cracks. That's what all these little cracks are right here. So that would have been a simple solution. 3 days later, so they did a trial pour, and then they wanted to adjust their mix, so we required one more trial pour, and we allowed them to do their test pour in the legs of the mix. So the in and out of the roundabout does not have fibers in it, but these legs do have fibers in them, and just these corner areas, and then the roundabout itself does. So the roundabout was poured 3 days after the legs were poured, and we did some early analysis or observations of the cracking. So 3 days later, R5 and R7 in the red here, those were the first 2 cracks that appeared visually in the roundabout. One of them, I talked about that notch. One of them cracked off the notch. One of them didn't. 917 the next day, R1, 2, 3, and 8. So the dark blue were the next cracks that appeared. And then 918, R4 and R6. So those were the next cracks. So, it kind of cracked, in a way you thought. It's just taking that circle and splitting it up. First it almost split it in half, and then it's that are observed through 11-18 of the first year. And just a few pictures from early on, these first observed cracks. These were the notches that were installed, and you can see the crack initiated off of that notch. I think you can see it also here, all the way over to here. This just happens to be, one of these cracks, and you can, if you look closely, you can see the fibers reaching across that crack. Our hope is that the fibers are going to hold it tight and prevent the faulting. Just a few more pictures. Here's the notch, here's the crack. So even though we had it there, the concrete's going to crack where it wants. So some interesting lessons learned. This is one of the legs. You can see they didn't put any joints in those legs and they cracked it as we would expect. So, and now I will transition it over to Peter to give you an update on how it's performing.
Great, thanks very much, Maria. A good lead in, and it's always fun to hear about the history and the why you did this project. So same photograph that Maria already showed you. One of the things to point out is that this thing doesn't get an awful lot of traffic, and maybe that's a good thing. But I keep planning to get out there at some stage and have a look. Apparently there's a pretty good quilting store nearby, and my wife is very keen to go, but we haven't got there yet, especially last year when we've been locked down. Maybe 2021 we will be there. So just a little bit more background information. 170 cubic yards of mixture on a 6-inch aggregate base. The width of the pavement was 16 feet and the thickness was 7 inches. Remember that 7 inches. We'll come back and discuss that at the end, I suspect. All right, and as Maria has already pointed out, basically a whole bunch of concentric circles. The truck apron did have joints in it and dowels to hold it all together. Then the green is the pavement itself with no joints in it. And then the legs and the filabits. Just a photograph of the same pieces, the colored truck apron, and here's the pavement that we're actually really interested in. And what is apparent here in this photograph, I'm not sure when it was taken, is again a fairly big crack here, which is very clearly faulted fairly significantly. And we've got some numbers on that coming up in a little bit. A few details on the mixture: about 620 pounds of binder, which is probably about right when you are putting in increasing amounts of fiber. So yeah, that number is not surprising. You got 20% fly ash, which is great for all the durability aspects, ASR, oxychloride prevention, heat of hydration mitigation, all of that good stuff. So I'm delighted with that. The water cement ratio 0.42 target, which is again in the range of where we normally recommend it. And the fiber content was at 6 pounds per cubic yard. Target air 7%, target slump 2.5 inches or thereabouts, which again for a hand place system is a little low, but not unreasonable. The fibers themselves were a proprietary brand from a commercial supplier, and they were a mixture. Partially cellular, I think there were cellulose or different versions of polypropylene, high stiffness and lower stiffness polypropylene. The idea being with the mixture is that some of them will help you with the plastic shrinkage cracking, and some of them will help with holding the main cracks together. 2 inches long, aspect ratio of 83, which are consistent with the DOT requirements. A couple more photographs of the construction. So it was, as it came out of the truck, it did look fairly dry. And you can see the fibers poking out of it, which is fine. But the finishing actually doesn't look too bad. Which is finished pretty quickly. And the finishing seems to have gone reasonably well. I don't think the contractor was complaining an awful lot. Maria already alluded to the wind was howling and a moderate relative humidity and a moderate air temperature. But it did seem as though that despite their best efforts, some of the curing compound didn't quite make it onto the pavement. And so there were some places in the system where there's some plastic shrinkage cracking happening. And again, this is more of an issue of building on the plains on a windy day. Maria also told us a little bit about these notches that were cut all the way around the circle on the outer edge, 4 feet apart. And again, 15 inches long, 1.5 inches thick, which we can talk about it at the end, but one of the things that we want to raise is what would we do different? And I'm thinking that if we try notches again, when we've got a 7-inch slab, 1.5 inches may not have been enough, and maybe even 15 inches isn't enough. So that's something that we can debate during the Q&A section. Fresh properties of the mixture ranged between 5 and 9, which is not bad, maybe a little high on the top end. Slump range between 3.5 and 3.75, which again is probably about right for hand place systems. Water cement ratio from batch tickets was 0.4 to 0.41, which is great. Strengths ran at 28 days. Compressive strengths ran at an average of 4,800, which is more than enough that we would normally expect for a pavement type system. Flexural was 590, which again is pretty reasonable for this type of mixture. The one thing that does raise a little bit of a flag is the specified residual strength was 175 psi. The measured results from cylinders beams taken at the test site during construction was that we were only getting 130 psi. This is data collected from University of Minnesota in Duluth. So that's another thing that we may want to revisit is the difference between the trial batches and the real concrete. Also, the slab thickness measured using cores was in the range of 6.1 to just under 7 inches. So again, we specified 7 inches, didn't quite make it. Whether that's significant or not, I'm not sure that it plays a whole lot into the crack pattern. It'll be interesting to watch this thing over the next 20 years just to see how it deals with the traffic. Again, the traffic on here is pretty minimal, so I'm not too worried about that one. So the surface itself is generally pretty good. And as I said, the contractor didn't complain an awful lot. No signs of any durability problems so far. So things like decracking, ASR, freeze thaw are not an issue. There are signs of some of the fibers poking out, and particularly here's one of the flexural beams from UMD, and you can see the little fibers poking out of it. So there were lots of fibers, and they seem to have been pretty well distributed. The contractor did a great job of making sure that the fibers were uniform throughout the mixture. One of the other toys that we played with, Minnesota DOT had just acquired the Mira, so they brought this device out. It's an acoustic device that does a really good job of picking up changes in density of the system as a function of depth. And so what this thing is picking up, here's at the top end is the surface of the concrete. The bright red area is an indication of the thickness of the slab, and it's typically 6 to 7.5 inches, which again is consistent with the coring numbers. And then there's a secondary reflection, which is the bottom side of the foundation system. So again, fairly consistent information coming out of this thing. It also does pick up a crack here. So the key question in everybody's mind, how does this thing crack? And so I've got 3 images here, and we'll cycle between them just to illustrate what happened. This is the first set of cracks that were resolved within probably a month of construction. So this is in 2018. And it's basically the same information that Maria already indicated, is that we had 8 cracks right up in the beginning. To me, it's kind of telling that 3 of them are very close to the cracks that occurred in the legs that Maria already talked about. So it's not uncommon, and here we see it again. Whenever you have an adjacent concrete system with a crack in it, it's not surprising for that crack to reflect through, and that's happened on the northeast corner, northwest corner, southwest corner. Southeast, it's a little bit off. But that in this case, there were 2 little cracks in the legs as opposed to 1 big one, so that may have helped spread the love around a little bit. So some cracking in the first couple months. A year later, we went back out there in 2019, and now we had 18 cracks. And again, interestingly, that they're not uniformly distributed. Concentration of them around the south end and the east end. And then a couple more sort of focused again around where they first started out next to the leg cracks. So, you know, we more than doubled the number of cracks in the first year. And again, that's not surprising. We're starting to put traffic onto this thing. It's been through a winter and all of the expansion and shrinkage related issues. In fact, these readings were taken in fall, so it also had a summer of temperature variations to help get things moving. Then 2020, I did manage, despite COVID, we did manage to get a crew out there and did it again. And again, I'm going to flip between 19 and 20. Now we've got 28 cracks, well, 27 radial cracks, and now we've developed another one, which is effectively a longitudinal crack here on the southeast corner. So now the cracks are more uniformly distributed. And I'm really looking forward to getting back out there in the fall of this year to see whether or not these are stabilized or if we're going to grow a couple more. Just before the webinar started, I got some dimensions from Maria and worked out the average spacing of these cracks is about 16 feet based on the center line. Sorry, the center of the pavement. So if we would draw a line around the middle of the green area, it's about, on average, 16-foot spacing. And that's actually not an unreasonable number. I mean, we typically design pavements with 15-foot, 20-foot saw cuts, because that seems to be about the natural spacing that cracks occur in a pavement such as this. We've also built here in Iowa a quarter-mile section of pavement with no saw cuts, a little bit more fiber in it, a slightly different fiber, and that thing is also starting to, it's in its third year now, is also beginning to sort of crack out at about 15 to 20 feet spacing. So probably the one that concerns me is this longitudinal crack, and we need to keep an eye on that and be worth going back out there when the weather gets better and having a close looking at that as to what may be the cause of this longitudinal crack. So just to refresh, some cracking early on, doubles up in the first year, almost doubles again in the second year. We will see what happens in the third year. Now, the consequences of cracking. So what? In a way, I'm not surprised we've had cracks. These type of fibers, I would not expect them to have sufficient stiffness to prevent cracking. What they will do is help us distribute the cracking. And the other hope that we have for these things is that they help keep the cracks tight so that we're not going to get load transfer issues. You know, the idea being is that if we're depending on aggregate interlock, if the crack opens up too much, we lose that aggregate interlock. And so the idea of the fibers is that we keep things tight enough that we still have the load transfer through aggregate interlock. So we did have a look at this. Again, a couple of photographs similar to the images that Maria had. Here's the saw cut, the notch, and here's the crack ignoring us and laughing at us. Some cases it did go through the notch, and in other cases it did not. So here's the data that was collected. The DOT went out and helped us with measuring crack widths, and they also measured load transfer efficiency, and that's in the next couple of slides. So in year one, that's the blue lines, we can see we've got all 18 cracks already identified. The first 8 are the ones that cracked out in the first couple of months, and those are all pretty big. And this is following that fairly typical model that we see. Early cracks tend to be dominant, and they keep growing with time, and they end up being pretty wide. And here we have a fairly high number of 5 to 10 millimeters in the first year, 10 millimeter, even up to 15 millimeter in the second year. For the cracks that formed in 2020, those are a lot tighter. So again, these later cracks are indeed staying reasonably tight. So an interesting distribution. Once again, I'm really looking forward to seeing how these change in the third year when we can get back out there. DOT also ran FWD and measured faulting for us and the crack widths. And we managed to develop this plot, which is crack width against load transfer efficiency. And again, this is the number that we're really worried about. If we take a pass-fail limit of about 70%, what it's telling us for the systems that we have here, for the curve that we've managed to draw through this, is that we need to be a crack width of less than 3/4 of a millimeter. That's pretty tight. And if we go back to the previous figure, you can see that it's really only the very much later cracks that are still under that 3/4 millimeter crack width. So we're getting fairly significant LTE numbers on all of these early age cracks. And again, whether that progresses and gets worse, or if it's stable from here on out, I don't know. The other part of it is with cracks as wide as this, we may start finding with water penetration that the foundation may start getting eroded. So we may actually find LTE will get worse if our support system is getting attacked. All right. So a total summary of all of the things that we've seen. Fiber distribution, concrete workability, the contractor did a really fine job of preparing a mix that was constructible. It's eminently doable. So that's not an issue. No signs of material distress after 2 years. Again, not surprising. A low water cement ratio, a good air void system, a stable aggregate. Those are the things that normally worry us. None of those were concerns going in, and indeed, they're not a concern so far in the life of this pavement. Crack propagation is interesting. As I've already said, we've got quite a lot of cracks, on average about 15, 16 feet apart. Some of them have got to be pretty wide. I didn't plot up the data, but the crack, some of the crack widths, in fact, I think we've got it here. Yeah, the crack widths up to about 10 millimeter, and faulting on some of those very early wide cracks, faulting is in the order of 5 to 10 millimeter. Typically 5 millimeter, but there's a couple with, 10 millimeter fault is actually something that you're going to feel when you're driving across that. So that's the one that we need to keep an eye on over time and figure out how do we do better in the future. Load transfer efficiency is a function of crack width, and that's not surprising, but again, it's always nice to be able to plot some data and confirm what is intuitively correct. Only 8 of the observed cracks were initiated from the notches. So again, the success of the notches, yeah, not so much. And maybe that's one of the things we need to talk about is how do we motivate those to crack open a little sooner and reduce the dominance of the early age cracks. So that's the information we have so far. The work is ongoing. We're due to do another analysis in the fall of this year and write up a final third-year report, and that will be the end of the contract. I'm assuming we're going to keep an eye on this thing through the foreseeable future anyway, just because it is intriguing, and we want to learn from this thing going out into the future. The second-year report, Maria, I believe is available on the NRRA website for those who want to look at some of these data. So, I've lost a slide. Here's where I want to throw it out. The question I asked, and it's worth us debating, and let's see if anybody from the audience has any input on, Maria, would you do this again? And if so, what would you do differently?
Well, if you're asking Maria first, I would like to try it again.
Good.
Would I put the notches in? Over the course of the last 2 years, I've went back and forth on that. I do agree with you that we weren't, when we originally started, we weren't going to put any notches in. So that was kind of well, we'll see if we can encourage them a little just by trying to do something, but I didn't want to take away from the integrity of what we were trying to determine. So putting in deeper notches and forcing the cracks to go there, you know, I don't know, it's counterintuitive. I could go either way on the notches, but I agree if we really want them to serve their purpose, they should be deeper.
Right. I would target T/3.
Right.
And maybe a little longer. In fact, it's something I meant to try and dig out, is that European practice on CRCP is to do something like this. And I wanted to go into their records and see how deep and how long the notches they put in. But they've had some pretty good success with that model.
You can have that for year 3 report.
Okay, I'll put it in
And
there.
future recommendations.
There we go.
So yeah, I don't know. I could go either way. They did go out. We didn't really mention it after the first winter, or before the first winter, the district did go out. One of your pictures showed it, and they sealed those first 8 cracks.
Mm-hmm.
I do not believe they've sealed the cracks beyond then, but I haven't been out there in the last year and a half either. So Rob may be able to answer that question also. Or if you
we
can
have to go from the
document it from your pictures. But
yep.
Well,
yeah. What about the mixture? Would you change that?
So I don't know if I change the mixture. And one of the things that maybe the terminology, we required them to demonstrate to us on paper that the fiber dosage would, by calculations, would make 175. Unlike at Minroad, where we made them trial batch the mix to do residual strength, we did not require them to do the residual strength testing to demonstrate it made 175. So we did not have preliminary beams that showed at 6 pounds it would make it. So that was, to do it again and asking for 175, we probably should have them demonstrate it.
I agree.
You may find achieved it.
You may find you need a little bit more fiber and possibly a different conversation of that blend. But yeah, that's another one I'd follow up on.
Right. And if they did have that, would we see something different? Would we be seeing the same frequency of cracking? Maybe not. I don't know. Would we see the faulting that we're seeing right now? Because there is definitely faulting out there.
Oh yeah. Yeah, you can see that in this photograph. All right. Those are all the discussion points I had. Lauren, any questions?
Yes, we do have a couple comments just in the Q&A box here. The first question was, could I get a copy of the submitted QC plan for fiber distribution? And I answered that, if we can, I can post it to the project page.
I would say that I can get Paul a copy of that, but I prefer not to post it to the page because it's the contractor's plan.
Yep. Great. And then Paul also asked, seems like, I think this is a comment, seems like there are a lot of options in fibers these days, and perhaps a higher residual strength can be achieved for less concrete without mild steel. So I don't know if you have any responses to that. I'm not sure what that means because I'm not the concrete technical expert here.
Yeah, I mean, steel will give you the best residual strength, but yeah, the fibers that we have available to us today are doing a far better job than they were 10 years ago of starting to get towards that same performance. And again, there's some very good guidance on what residual strength you need, how to design a pavement based on that residual strength in a document published by Jeff Ressler. I would strongly recommend it. If you need a link on how to get that document, give me a shout. It's on the CP Tech website.
Yeah, I think our target number was good. We just did not have the luxury of having them prove it out, because I know to get the testing done for Minroad, they actually, I think, did the testing down in Georgia or somewhere, just as it worked out. And so we have some liberties when we're doing the research at Minroad that we didn't necessarily have on this project. So
And time is always a constraint.
and time, yes. Go
Okay,
ahead,
and
Lauren.
then Tom also had the comment that his visits to the site reveal much heavier truck traffic than you mentioned, especially during harvest season.
Yeah, that's a good catch. Again, I'm feeding data I was fed. So yeah, if you got better numbers, Tom, let me have them. Get the report.
And we maybe could ask the district if they've checked the traffic since then, but as I showed you, that's a shortcut across, so they don't have to go Highway 14. So as we always see, you build it and they will come. So
and that's where I was headed, is that I think the traffic data predates the circle, and you probably find it's doubled because now this is an easier way to go.
Yep.
And then Paul asked, are the cracks being sealed? And Peter, I know you mentioned that the first 8 cracks were sealed.
Yeah, that I don't know.
Okay.
Maybe Rob could pick that up.
And then Tom asked, what are the thoughts on the C1609 test? Beam testing did not match results from as-built pavement.
Yeah, very good question. What Tom is referring to is the test that determines that residual strength. So I ripped it out of a previous version of this presentation. It's basically a flexural beam where you monitor crack width and vertical displacement under a flexural test so that you get data about what's happening to the concrete after it's cracked. And it is a notoriously difficult test to get right. It's extremely operator and equipment sensitive. So there is certainly a potential for, the data is an artifact of the test as opposed to being an artifact of the mixture. But there's also an issue that if you haven't tested it before, it's quite possible that in paper it worked, but when you change your aggregate system or you change your water cement ratio a little bit, it could drift off pretty fast. So yeah, unfortunately, 1609 is a bit like the slump test. It's a horrible test, but it's the best one we got right now.
Okay, and Ben asked if you did limited saw cutting, would cutting this in quarters make sense?
I have no idea. Probably not. Again, what we saw is that it broke into 8 pieces, and those 8 joints are dominant. So if you saw cut it into 4, those would be more dominant. I think if you did that, you'd have to put dowels in. That's an interesting thought. I don't know, Maria. You're better at design than I am.
Oh, I don't know about that. I think your guess is as good as mine. I mean, and theoretically, if it would have cracked at all the notches, would any of them have been dominant? Could we have rode a truck over it to try and initiate more of the cracking?
Same as you
Lots
did
of
in
different things we could do. Yeah,
Yep.
Your guess is as good as ours, so that's why we tried it.
I thought I saw a memo. I can't see the Q&A because I'm sharing my screen, but I thought I saw something go past. Rob answering the question about joint sealing. Maybe it was in the chat.
Yeah, I just got a comment in the chat from Robert Golish. The joints have not been sealed since the initial ones that I could see went out there last. So it sounds like they have not been sealed.
Okay.
Okay. And let's see. Do we have any cost information compared to conventional roundabouts?
We did not do that comparison. The district may have looked at the cost. I think that's something certainly we could, you know, dig up for Peter and have that for the final report. Might have to remind me, Peter, but the district has built many concrete roundabouts the last few years, so we certainly could do a comparison between this one and the others.
That'd be a good idea. Yeah.
Yep.
Yeah. Any thoughts on the role aggregate gradation might have played on workability?
Now you get me going down a whole long rabbit trail. I'm a fan of the tarantula curve. So my experience is that if you get a good gradation within tarantula, you will have great workability. And when we say workability, it's both that primarily the response to vibration. Again, this is hand placed, but in slip form paving, you know, we want it to be wet when it's inside the paver, and we want it to stand up straight afterwards. You may find if you went to a slightly more uniform gradation, it may be a little bit wetter. The approach I'm taking for proportioning mixtures with fibers is that to compensate for the surface area of those fibers and for their locking up tendency, you need some additional paste. Now, the section that we built in Northern Iowa with the jointless straight line section, I took the mix that they had used on the rest of that contract. I think I added about 50 pounds of cementitious to the mixture, and that worked really nicely. The mixture was, and this was slip form paved, and the mixture went down really easily. The contractor started getting grumpy about the amount of cement he was having to put into it. And incidentally, I think at that stage, he was running at about 550 pounds per cubic yard. He tried to cut it back to about 520, and the workability fell off pretty quickly. And they still managed to finish it, but it was a little bit more bony, and the finishing crew started to gripe pretty hard. So the 620 that you had in there, to me, was more than enough. I think we could even cut that back some.
Yeah, we did allow them to only put 3/4 inch maximum size aggregate in this mix too, where most of our paving mixes have 1.5 inch coarse aggregate in them also. So it was just one sand and a quartzite, which is a very angular coarse aggregate, was actually used in this mix design. So this one did not have the tarantula requirements, primarily because it was going to be a hand placement. We knew that we wanted to, you know, not add some of those additional elements to it. But when we picked the 175 and, you know, modified our specs to allow the higher cementitious, I think 615 max, we looked and learned from the different test cells at Minroad, where we did the 3 different dosages of fibers. So lots of good questions though.
Yeah, I've actually got a student fooling around on, you know, how to do mixed proportioning with fibers in it. Still pretty early days, but this idea of a little bit of extra paste to cover the fiber seems to be working philosophically.
Okay, and I've got 2 other questions and a comment. So Matt asked, to improve the workability of the mix, do you think it would make more sense to consider a glass fiber for this application as they use in Europe? And I think in response to that, Tom just added that we do have a new NRRA project to develop better fibers for pavements. But maybe you still want to respond to that question.
Yeah, I mean, glass is fabulous from the point of view of stiffness. To me, that's the critical part about any fiber system, is that, you know, the way to think about it is that if you've got a collection of books that you're trying to wrap an elastic band around them to hold them together, if you use a thin, very stretchy elastic band, the books have got to move quite a lot before the elastic band starts doing its work. But if you've got a thick, hearty truck type bungee around it, they don't have to move very much before the elastic band is doing what it has to keep it together. And the same applies in here, is that low stiffness fibers have to move a lot. So that's why they don't prevent cracking. What they do is help influence the amount of, the width of the cracking. And the higher the stiffness, the better off we're going to be. And glass is fabulous from that point of view. A couple of challenges with glass is bond, because glass by definition is pretty smooth. The other big challenge is that conventional glass fiber gets eaten by the cement. Now you can get e-glass, which is a little bit more resistant, but I haven't read too much about how those things actually perform over the long term. Because in a way, glass is not very different from pozzolan. So over time, it may actually react to form more compounds that may or may not be deleterious at the end of the day. So I know it's heresy to say, but asbestos was the best fiber out there. It was non-reactive and extremely stiff. The health hazards make it impossible for us to use nowadays, but from a pure engineering viewpoint, it was great stuff. And that's why it works so well for so long. So yeah, I look forward to the work that NRRA is going to do on that.
And the last question that I have here is also from Matt. Does the longitudinal crack appear to be a top-down crack?
I have no idea. Maria, Rob?
We've never cored them. So unless the mirror can magically tell us something, we do not know for sure.
Yeah, the mirror won't be able to pick that up. It's more oriented towards identifying horizontal flaws, not vertical ones.
Yeah. So I would say that might be a consideration for year 3 if we want to core through any of them or not. Discussion with the district.
The other question I would have is to revisit the foundation system. Was it as well consolidated under there as it should have been? There's no way to tell now, but
Right.
again, a core will help a little, as that if there's a void underneath the concrete, that'll tell us something.
Yeah, Rob did add a couple notes here that the cracks are very tight. Most of them are. The longitudinal crack was very difficult to see, was another comment made, because Rob was out there when Tom and Mike and his name's escaping me, Peter.
Ahmed.
Yeah, Ahmed. So.
Yeah, kind of sorry that Ahmed has escaped. He's gone to Caltrans. So I'm going to have to find someone else to come up here in the fall.
So yeah, lots more to think about, and it was fun.
Yeah, it's intriguing.
Well, great. That brings us actually right to the top of the hour. We're 1 minute past now, so we did great on time. And I believe, well, I included the URL to the project page in the answer to my first question there. So if you want to get in contact with Peter or Maria about this project, their emails are listed there, and you can email the TAP even too if you'd like to. But I will close this out for today, and we can keep going with our Tuesdays. Thank you very much, Peter and Maria, for your presentation and for all that information and the good discussion there at the end too.
Great. Thanks, everybody.